the next speaker of this morning session is Kelvyn Welsch. Kelvyn, my PhD student. Actually, he's my student since the undergraduate. And despite of I to say that this paper is very easy, which and we will present anyway. So he will speak about cluster expansion and decay of correlations for long-range Ising model.
Good morning. My name is Kelvyn Welsch. I'm here from the University of São Paulo. I'd like to thank you all for the presence here. And so today I'd like to talk about the long-range Ising model, especially what are the ingredients that we need to establish the convergence of the cluster expansion and obtaining also the decay of correlations. So my talk will be organized in 5 parts. I will start by providing a historical motivation. Then I will state the main results of our work in a precise manner. Then we will enter the main section. Well, I'll try to convince you that the usual contours, they have intrinsic difficulties in order to prove our results, the convergence of the cluster expansion, so on. And this will lead us naturally to the definition of multi-scale contours that are more adapted to the long-range setting. And finally, I will conclude and talk about some open problems. Okay, so let's start with the history. As many of you already know, the Ising model was introduced by Ising himself in his PhD dissertation around 1925. And there, he proved that the model does not undergo phase transition in one dimension. And also, he extrapolated this result for other dimensions, and this became a common belief in the physics community. Until 1936, when Peirce proved that the Ising model indeed has phase transition for a dimension greater or equal to 2. And in order to prove this, he introduced geometrical objects that now we call contours. And these contours, they proved to be very, very, very useful to prove a lot of things. For example, in 1966, we have this paper by Ginibri, Grossman, and Welsch, and there they proved phase transition for a wide range of models. For example, for models that have polynomial decay, so the interaction goes like their 1 over their distance to the power of some alpha. In order for the models to be regular, we always need that alpha must be greater than the dimension d, right? And in this paper, they managed to prove phase transition for alpha greater than d plus 1. So all this region here, they proved phase transition when d is greater or equal to 2. So big part of the region where there is regularity, they proved the phase transition. By correlation equality, so we already know that there is phase transition here, but until then, there was no contour method that gives us more information about the configuration and so on. Okay, but what about one dimension? Ising already had proved that there is no phase transition for the nearest neighbor model, but 2 years later, Welsch proved that, in fact, there is no phase transition even for long-range interactions when alpha is greater than 2. So for d equals 1, we must have alpha greater than 1. And in all this region here, Welsch proved that there is no phase transition. And 1 year later, Dyson proved that there is phase transition when alpha is between 1 and 2, strictly less than 2. So there was this question, what about alpha equal to 2? Is there or isn't there phase transition? This question became open for some years. Meanwhile, the contours kept developing. So its development reached its peak around 1975 by the hands of Pirogov and Sinai. So Isabella Stuhl mentioned Pirogov-Sinai theory yesterday, and it's a very important theory which gives us a lot of information about phase diagrams, phases, states, configurations, so on. And there was an attempt to extend this theory for long-range interactions by Park in 1988, but he only managed to prove this extension for alpha large enough. So, for example, alpha larger than 3D plus 1. Okay, but back to the question here. This was answered in 1982 by Froelich and Spencer in order to prove that indeed it has phase transition, right? So they introduced another version of contours, and this inspired a lot of subsequent works. So, for example, in 2005, Cassandro, Ferrari, Merola, and Presutti adapted these contours in order to not only deal with alpha equal to 2, but a larger region. Then they also attacked the random field external model, right, and proved phase transition. Then they also studied typical Gibbs configurations. They proved the convergence of the cluster expansion, studied phase separating point, and also phase separation, like Pico had talked yesterday. Okay, then in 2025, Lucas Afonso, Rodrigo Bissacco, Eric Endo, and Satoshi Handa, they, inspired by the work of Froelich and Spencer, they defined a version of the Froelich-Spencer contours for dimension greater than 1, right? And they could prove phase transition, prove nice entropic bounds, and so on. And then, with the right notion of contours, we could prove also a lot of results. So, for example, we proved phase transition in the presence of a random field, external random field. Then we proved phase transition for another models than Ising, so Potts model, clock model, and so on. We proved phase transition and also the cluster expansion to the one-dimensional model. Corsini will speak about this in the next talk. And in this talk, I'd like to speak about this paper here, joint with Lucas Afonso, Rodrigo Bissacco, João Maia, João Rodrigues, where we, as I already said, we proved the convergence of the cluster expansion and the decay of correlations. So this is a diagram of the correlations. I'll explain it in more detail later. So to the main results, the background is the following. We have the as configuration space this one. So in each site of ZD, we may have -1 or +1 as the usual Ising model. For finite volume, the configuration space is -1 +1 to the lambda. And we have boundary conditions, omega. So for the configuration sigma, the Hamiltonian is given by this expression here. So JXY is like a coupling between the spins in X and Y. And JXY may be chosen, but they must satisfy some conditions. For example, we usually ask JXY to be non-negative in order for the model to be ferromagnetic. And also, we ask this sum here to be finite so that the model is regular and things don't start blowing up. Also, we will need the all plus configuration, which will denote by sigma plus, which is just the configuration that it's +1 everywhere. Okay, so there are some models that fit in these conditions. For example, the usual nearest neighbor Ising model, in which JXY is just some constant J, positive, if X and Y are neighbors, and 0 otherwise. But in our case, we will study this model here, where JXY is some constant also, greater than 1, over the distance between X and Y to some power alpha, and alpha must be greater than D in order for the model to be regular. Okay, so the rest of this talk, I'm going to use this model here. So, as Van Etter talked a lot about Gibbs measures, so The finite volume Gibbs measure is defined by this expression here. So we have the Boltzmann weight, which is E to minus beta times the Hamiltonian of the configuration. And have this the normalization constant, which is the partition function, which is the sum over all the weights. So for the plus boundary condition, we just write mi plus and z plus. And it will be very important for us to consider this normalized partition function, which is just the partition function, but the energy of the configuration will be seen as relative to the L plus configuration. So we will put the L plus configuration as like the reference level of energy, and then the corresponding partition function will be z tilde here. Okay, so the infinite volume Gibbs measure are well defined for example, the L plus boundary condition. And for any local observable, we can define expectation value here. And then we define also the truncated correlation, which is the mean of the product minus the product of the mean of the two observables. And when one of these observable is characteristic function of, for example, sigma x being equal to -1, we just put the event here. So this is what how we denote it. So the main theorems are, in first place, this one. So for the long-range Ising model, if beta is large enough, we can construct a polymer representation for which the cluster expansion is like this here is absolutely convergent. And with this result, we can also prove that for beta large enough, there is some constant such that the truncated correlations are less or equal to some constant times the coupling between x1 and x2. Okay, so now let's start dealing with the problem. Why can't we do this with standard contours? So just a brief review about what are these standard contours. So here I have some configuration. A point x is called incorrect for this configuration when sigma y is not equal to sigma x for some y in the neighborhood of x. So for example, this point here is not incorrect because all of its neighbors are plus, but this point here is incorrect because it's minus, but there are neighbors which are not minus, also for this one. So if we highlight all the incorrect points, we end up with this drawing. The set of all incorrect points are called the boundary of the configuration. And the usual contours are just the connected components of this boundary. So then this will be one contour, this will be another contour, and this will be another one, right? So this is just the definition of the Pirogov-Sinai contours. The support of a contour is just the geometrical information about where it lies. So it's a contour carries the geometric information, also the spins, but the support is only the geometric information. Okay, so now suppose that we have some subset of ZD, like this one, A here. We will call the volume of A when we fill all the holes. So the volume of A here will be this one. This is the volume of A. And this allows us to define the notion of externality for contours. So a contour is called external if it's not contained in the volume of any other contour, right? For an external family of contours, their volumes are disjoint. And this allows us to interpret contours as particles. So one of the advantages of dealing with contours is that we can treat them like particles, right? And we can use a lot of tools from particles and apply it to contours, right? So here, as an example, we have three contours, gamma 1, gamma 2, and gamma 1 prime. These blue contours, gamma 1 and gamma 2, are external, while this one is not, because it's inside the volume of gamma 1, which is this region here. So, okay, now given an external compatible family of contours, we may define the Hamiltonian of this family using the corresponding configuration. And as we are we would like to treat them like particles, we want to express their Hamiltonian as a sum of one body energies and two body interactions. So if we do that, the interaction that we call phi2 will be the energy of the configuration consisting of the two counters minus the energy of the configuration consisting only of one of them minus the configuration consisting only of the other one. For the long-range Ising model, this interaction here can be written in a quite clear way. So it's here. It's minus 2 times the sum of x in the volume of the first counter, y in the volume of the another counter, of the other counter, of the couplings jxy, and sigma of x and sigma of y must be minus 1. So this is the pair interaction between two counters. Okay, now let's define a kind of restricted ensemble. We have omega 2 ps, which will be defined as the set of all configurations that have only two counters, gamma and gamma prime, which are also external. And we may define the interaction, the phi2 of the configuration, as the interaction between these two counters. And what I will going to show you is that for the long-range interaction, this potential here, this interaction is not stable. So the infimum in this restricted ensemble is minus infinity already, right? It's not very difficult to see. So we are going to define a sequence of configurations such that phi2 will go to minus infinity. So what will be these configurations? We'll have a C of plus and two columns of minus. The first one that we'll call AN, which has a height of n. So there are n spins here, which are minus, and another column with the same height, which we'll call Bn, right? We have this distance between them, which is h. This will hold for any h, so it's not the problem. And the sequence will be indexed by this capital N here, which is the height of the two counters, which looks like two batteries, but okay. So the h just must be so that the two counters are disjoint. And then the interaction between them will be minus 2 times the sum of x and y of jxy, such that x is in the volume of the first one, y in the volume of the other one, and such that the spins are minus 1. So we are summing over all the pairs. So x here, y here, x here, y here, all the possible combinations. But it's a negative sum, so we can, if we drop some terms, then to be greater, right? So we can bound by minus 2 times the interactions only between pairs in the same height. So this with this, then the second with the second, and so on, so forth. And then by the translation variance, these interactions will be always the same, and there will be capital N of them. So what we have at the end is that the interaction is less than minus 2 times n times this j, which is positive. So we see that this goes to minus infinity. Okay. So what we conclude is that standard contours do not provide a stable particle representation for long interactions, right? So in like continuum models, stability refers to this about the pair interaction must be bounded below. So it's not the case here. And this motivates a multiscale notion of contours. So let's define them. So the multiscale contours will also be elements of some partition of the boundary of the configurations, but not in connected components. So we'll need to introduce what is an MA partition. So we fix real numbers m, which must be greater than 1, and a, which must be greater than d. And for any subset, finite subset of ZD, a family of subsets of A is called an MA partition if it forms a partition, obvious. And also, for any distinct pair of elements, they must satisfy some distance conditions. So they must be far apart from each other, sufficiently far apart. And the scale in which this enough is considered is the scale of the volume of themselves, right? So we consider the minimum between the cardinality of their volumes. We have some constant here multiplying, also this power, this exponent here. Well, there is always MA partition of any subset of ZD, and we will always consider the finest one. So when we talk about the MA partition, it will always be the finest one. And for the finest one, these things here cannot happen. So we cannot have, so the contour may be disconnected, but it cannot be inside the different components of another contour. So for example, they are separated by gamma, so they must be two different contours, right? And this allows us to define labels, interior, and all the stuff. Okay, so this example here, which we have already seen, what will be the contours? Well, it will depend on the value of M and A. So depending on the value of M and A, it may be the fact that we have three contours separated, just like the standard ones, but maybe that we have one contour here and another one, or just only one contour that encompasses all the incorrect points. Okay, now to the main stuff. So the convergence of the cluster expansion is attained by the following three ingredients. The first one is that although we defined another version of the contours, we have still nice entropic bounds. So every standard contour is a multiscale contour, but we have a lot of new ones. So one may ask, okay, but how many? Well, the thing is that the quantities is also bounded by, it's also exponential in the volume. We'll see later. So we have this. We also will need to redefine the notion of externality. I'll talk about it soon. And also we'll prove that for these contours, they are stable. Okay, so if we define the collection of all contours such that y is inside the volume and their size is equal to n, then what we have is this. The number of the contours encompassing fixed point and with size n is exponentially n, so is this what we need to prove like parse arguments and cluster stuff. Okay, now the externality. Okay, so in the case we have short-range interactions, if we have a contour here and another one inside, then this contour does not know what's happening outside, right? It's like decoupled. The definition for contours in the short range case is defined so that it is all the contours have only have hardcore interaction, but they do not know what's happening, right? So they are separated. For long-range interactions, this is not the case. So externality condition does not make the same sense. This is not. So we need another definition. Geometric inclusion only does not describe energetic dependence. So we must define the effective volume, V tilde, which is the volume, but without the plus interior. So just the support of the volume together with the minus interior. And then we will say that a contour is plus external or just external when there is no confusion, when the support of this contour does not intersect the effective volume of any other contour. So, for example, here we have some contours. This first one, gamma, which is clearly external. But this contour gamma prime is also external in this case because it lies inside the correct phase. It lies in the plus interior. Although geometrically it is inside gamma, but it's also external because the effective volume of gamma is only this ring here. And gamma prime 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 is also external, but gamma prime prime is not external because it's inside the minus interior. So the V tilde of gamma prime is this region and also this one, this region here. So this contour is not external. Okay. But you may ask, how this affects the stability? So if we had considered this externality in the stability from the usual contours, it would be the same thing. Now we are considering more external families. We are weakening the condition of externality. So we are like putting ourselves in a worse place, but still we will prove stability. Okay. So now we define the analogous restricted ensemble, omega 2 MA, which are the configurations which has only 2 external multiscale contours. Also, we define the phi 2 of the configuration as the interaction between the contours. And what I would like to show you is that if A is big enough, so for example, greater than d plus 1 over alpha minus d, then there is some constant such that the interaction between the contours is always greater or equal to minus times this constant times m to the power of minus alpha minus d. And we can choose m as we wish, so we can put it very large and to be better. Okay, so consequently we have that the infimum of the phi 2 is bounded below from minus infinity, and we'll have the stability. And how do we do that? Okay, so we have we always have 2 contours, gamma and gamma prime. We always say that gamma is the smaller, right? We can exchange the names if we need. And we will define small v as the number of points in the volume of the smallest contour in each configuration. And the MA partitions like saying that for each contour there's like a safety zone around where there cannot be other contours that are bigger. It's important. Okay, but in this case, this distance is L gamma. So what we have is that if x is in gamma and y is in gamma prime, their distance must be always greater than L gamma. It's like a safe zone. Okay, now we will do this bound here. So let's suppose that we have a contour gamma here and another gamma prime. For each, this is the smallest one. So for each point x here, we must have like a circle around it that must be disjoint from gamma prime. Right? So for each point, we sum the interaction between this point and all the rest of the universe. It will have the gamma prime, right? So it's what we are doing here. We are, for each x, we are summing over all y that are far apart enough from x. The scale here is given by L gamma. And this will gives us a lower bound, right? Because we are summing more negative terms. And if alpha is greater than d, then we can show that this tail here is the order of L times L to the d minus alpha. So how we do that, I will do it like not many details because it's a standard computation. The number of points at some distance n of x is of order n to d minus 1. So if we put this information here in the sum, we have that this is bounded by the sum of all n greater than L of n to the power of d minus 1 minus alpha. Then to bound this sum here, we can use like the integral criterion. And if we integrate r to this exponent here, we end up with L to this power. So what? Okay. The condition that if alpha is bigger than d plus 1, then it's like the easiest part, right? So, okay. So in this case, we have that if we put this bound here, we have a constant that is being summed a number of v times. So we have some minus some constant times the size of the volume times the L gamma to d minus alpha. But if we put the definition of L gamma, we end up with this expression. Now we have the volume, so if this exponent here is not good, then it may go to infinity, minus infinity, right? But we can choose a so that this exponent is negative. Then it will work. And then we end up with this result here. So now we have stability. And so for the conclusion, what we have seen is that standard Pirogov-Sinai contours are not stable for longer interactions. Multi-scale contours provide the separation that we need, the entropy control that we need, and this stability. This stability, what is the basis, it's like the essence of the computations for the convergence of the cluster expansion. So the real computations are very technical, very ugly, but what's in the core is this stability thing. And this yields a convergent cluster expansion at sufficient low temperature. And as a consequence, we can prove that the truncated correlation satisfies this bound here. So for the diagram, what we had is that Jagonitzer and Swihart proved that in general, the truncated correlation must decay at least like the interaction Jx1 x2. It holds for any temperature, any external field, and for a field large enough, they prove that it's actually of the order of the interaction. But in general, they only could show that the truncated correlation is less than the distance times some exponent here. And it may be the case that this exponent, that it's actually an optimal bound. So for example, in the Thouless effect, the exponent here in this region, they can get so the Embry-Newman is for J going to infinity, but in this case, the exponent goes to 0. We don't know what happens in this case, but it may be the case that it goes to 0 also. So for beta small, we have Eisenman-Fernandes and Newman-Spoon results that the truncated correlation is also in the order of Jx1 x2. And our result tells us that in this region, the truncated correlation is also of the order of Jx1 and x2. So together with the result of Jagonitz and Swihart, we have also this thing here. Okay, so thank you.
So comments or
so thank you for the talk. So I just have one small question about the MA partition, because you chose A and A as D plus 1 over alpha minus D, right?
Yes.
So do you use the same value for A in order to guarantee the convergence of cluster expansion?
Good question. No. For the convergence, as Van Etter said, here we are mainly concerned with the case where alpha is between D and D plus 1. But in general, what we need is like A is some constant, we can choose 3 times D plus 1 over the minimum between alpha minus D and 1. So this is the one thing that works.
Yeah,
but it resembles a little the choice here.
Yes, I understand. This is the same value of A as in the Q state model, the POTS
Yes,
model,
yes,
clock
yes,
model
yes.
of the Gilberto's results,
Yes.
right? So do you expect you need the same A in order to extend the cluster expansion for the POTS model, for example?
I think so.
I see. Nice.
Other questions? Oh.
No.
So, because this the Ising model at, with long-range interaction, polynomial interaction, it's absurdly difficult, let's say, and it is strange at the same time because long-range ferromagnetic interaction should be give, for example, phase transition much easier than
Yes.
the nearest neighbor interaction. You can just use the Griffith inequality to prove that there is a phase transition. But if you try to prove the analyticity of the free energy for this model, then it's absurdly difficult, difficult. And your work is with the decay of 1 over r to the alpha, where alpha is between d and d plus 1, right?
Yeah, but all these things work for...
Yes, all that, but because there is this work by Park, it's a very old work that huge cited, that it basically treat the Ising model too, but when alpha is much bigger.
Yes.
Yes, 3D plus 1. I'm wondering, is there a reason? Because it should be the opposite.
So
it should
if
be
we
the opposite. More. It should be easier to treat a decay, a long-range decay, but it's not. So
yes, I wondered this also, but what I have noticed is that probably the problem is with this interaction because it's negative. So it's like the contours are attracting itself. So it's an attractive. And then what? So suppose that we have two contours, and we have a nearest neighbor interaction. Then we slowly turns on the long-range interaction. Then the energy, the interaction between them, will actually be lowered, right? So the Boltzmann weights are E2 minus beta the Hamiltonian. So if the energy goes smaller, then the Boltzmann weight gets bigger. So that's why things start to becomes difficult, more difficult to establish. But also another thing is that the total energy has also this one-body part. So actually there is kind of a trade-off about this part is negative, but also we have a larger one-body energy. So I think that to like deal with these models, what we need to do is like use these one-body interactions to treat the difficulties that because like it's just that the total energy is being split into these two sections, right? And because of this, the kind of way that it's split, it can we can get in trouble because of this, right? So we have to like borrow some of the benefits of the one-body interactions.
Yeah, but just right there the three regimes of the interface term for everybody. The F. The three regimes. You remember?
Okay. Yes, yes.
So what happens is the following. You know that okay, he will write, but the thing that you have to control the interaction between the inside and the outside, right?
Yes.
And this is very clear that It is in the literature already, but since it's long range, you have always to do what happens inside and outside for every point. So and we have this three regimes. You have alpha bigger than d, alpha equal d plus 1, equal d plus 1, and the real one, which is this one. And then you define this thing, which is the outside and inside, and this is the contribution of the. You see? And what happens that exactly here, you have this. Yeah, it's short range. So you see? So it is really, yeah. But I mean, during the calculation, this is. I mean, in all the papers, at some moment we stuck here. For Lucas, it was, I don't know, maybe 1 year something, that we are here and here and here, and some moments, and in the run. Okay, I will give a more historical review in my talk, but yeah, exactly this. Oh, oops. You see, when R is very big. Okay, Kelvyn wrote for balls, but what we do in the work, we have to study it for any finite set, and this more or less, you see, when you are in the okay, this is something is not right, because you have D plus. Yes. You have exactly. You have to exchange, because you see when because okay, for the physicist paper, they know this. If you are here, you are not really long range. This is kind of a lie. I mean, nobody cares if you do. I don't know 3. And another thing that about Parker paper, that the proof is using Kirkwood-Salzburg, so is you. Yes, but it's indirect. It's Kirkwood-Salzburg. He's not. That's why our proof has some value a bit. Yes, when you have this is Park. Yes, exactly. Yes, exactly. Yes.
Yes.
Right.
Just the alcohol, they cannot overlap. There is no long-range interaction between polymers. But you can try to do an answer polymer gas in which polymers are not at core, but also they interact. They interact even if they are far apart one another. Using this.
As the guy from Arizona, when you...
No, it just was because I tried to work in this in what you have done, but I didn't.
You don't have 10 students, let's say.
I didn't have so many good students, so and I'm not so good, so. But I was wondering if it's possible to do a cluster expansion for alpha d plus 1, but greater than this plus 1, using a polymer system in which polymer interact beyond the hardcore interaction.
It should work even for the connected contours.
I don't know.
Yeah, but this is one of the things that is very strange for us also, because even in the work of Pico, they managed to work, let's say, in dimension 1. They are here. So in the you see some kind of the opposite way that you see. Yeah.
Yes. Well, this is a very nice work, a very nice problem. But the problem is that physicists thinks why you should bother of long-range interaction, because there is fast translation. So
no. But this is a good point that was discussed with Arnaud. Because yes, we know by correlation inequalities that we have the phase transition for free, right? But if you do any kind of perturbation for any kind of field, you
random.
Yes, you have nothing.
Now, because once I asked to Presutti to, can you say something about the Ising model in more than one dimension with long-range interaction? He said, but no, with Griff inequality that there is fast transition. So
but you put any kind of field, you can nothing. You don't have to. In fact, that we try to read at some moment. We will try to come back here. We try to read big Compiani, and also we try to read this Bouvet and Kuskal paper also. And even in Brickmo Compiani, they at some moment they said, okay, we have this renormalization thing and so on. So you could ask about what is the core? Until where I can push, right? And they wrote, if you have a good system of contours, you can do. So maybe now it's written in the paper that if you have good contours, maybe you can do. It's not really. I mean, it's not really. It says what is written, but that is not dependent really in the let's say in the short range. It depends if you have good contours. It is written there. I'm not sure. Okay. Any more questions or comments? Carlos? No. So okay, let's thank Kelvyn again.
Thank you.
is a PhD defense. Is work like that. He has 50 minutes, and then the committee that I will present right now, we will ask questions that you can stay here, and then we will ask gently that you leave the room. So we discuss, and then I go out and okay, come back, and then this is the result. This is the way that we do here. So this is a PhD defense of Henrique Corsini. He is my PhD student. He is in the applied math program. And the committee is from Paulo from Federal University of Minas Gerais, Arno van Etter from Groningen and Netherlands, Aldo Procati also for Federal University of Minas Gerais, and Pierre Pico from XYZ. Probably he will say that I spoke some wrong place, but Marseille, for example, Marseille. You can choose. Pico has all the languages. He knows everything. So this is the committee and myself that I am president of this committee, and Henrique will describe his work that he has been done in the last 4 years. And the title of the presentation is the one-dimensional long-range ferromagnetic Ising model. So you have 50 minutes.
Thank you. So I'd first like to thank the presence of the examination board and the members of the audience. So as Rodrigo said, I'll be presenting on the one-dimensional long-range ferromagnetic Ising model. Right. So I mean, some parts of this is good. I mean, there's a small issue, I guess, because some of what I'm going to talk about, Kelvyn already did in the previous lecture, so bear with me. So I begin with an introduction, a historical introduction. So in the first moment, Lenz gave Ising what came to be known as the Ising model as a problem for him to study during his PhD years. He managed to prove that there's no phase transition in the one-dimensional case if the interaction is a nearest neighbor interaction. But he failed to tackle the problem if d is greater than or equal to 2, and he conjectured at the time that there's no phase transition, which was wrong. Nearly a decade later, Parles gave the argument, which is a seminal technique in the area, the Parles argument, using a contour construction. And I mean, I just mentioned Onzager's result because it's a very nice result. He gives a closed form to the pressure in the absence of an external field in the two-dimensional case. So. And then you can attest that the pressure is not analytic, and thus there's a phase transition, right? And the history of the long-range Ising model, I'm just going to mention the ones that Kelvyn didn't mention, which is first the proof that there is indeed a thermodynamic limit, which was from Galavotti and Miraclusol from 1967. And quickly, Ruel gave a proof that there isn't phase transition if alpha is greater than 2. Dyson proved in the same year a criterion that is slightly more general, very slightly, but just tackles, of course, alpha greater than 2. And Dyson gave a proof that there is phase transition if alpha is between 1 and 2 with a hierarchical model approach, which is also a very important technique in the area, right? And I mentioned Yagonitzer-Souyach because, I mean, I'll be doing decay of correlation. So it's worth mentioning the paper that shows that the interaction, the system is at least as correlated as the interaction times a constant which depends on the temperature. And then there's, it's a joke, the roaring 80s, right? A lot of important results came from the 80s. So, I mean, if you quickly look at this, the matter of phase transition when the decay is exactly 2 was open, and it was closed by Froelich and Spencer with a involved energy entropy argument, because if alpha equals 2, then at fixed temperature, energy and entropy are of the same size, so there's a competition there, a finer competition. And the most important thing in a way is their way of representing the system, which is fundamentally different from classical contours, right? And using the same expansion, Imbri, he gave a better definition to those contours, which was already contained in the one by Froelich and Spencer. It's the one I use as a sort of irreducibility criteria, and he provided a converging cluster expansion at low temperatures for alpha equals 2. His proof is highly dependent on alpha equals 2. It doesn't work I did try to reproduce his proof for different alpha, it doesn't work. But anyway, he proves that at low temperatures, the interaction, the correlations, 2-point correlations decay exactly as the interaction, right? Which is not the case for all temperatures if alpha equals 2, right? So in 1988, Eisenman, Chase, Newman, using percolation techniques and thus introducing a hypothesis from percolation, which is the interaction between nearest neighbors is very large. They managed to show that magnetization is not continuous, right? This is the Kondo effect, right? And in the same year, Imbrie and Newman gave a proof that there is a sort of intermediate decay phase right above critical beta C, so right below critical temperature. So the system is more strongly correlated in this temperature region. And to prove this, they more or less used all the machinery from Eisenman, Chase, Newman, and they need strongly that the interaction is large between nearest neighbors. So they conjecture a sort of a phase diagram using this thing, supposing that as J becomes lower, the structure remains, but there's no proof for it that I know of. I could be wrong. And then there's the matter of revisiting the construction, right? Because given a direct proof of phase transition, in a way means representing the system in an efficient way, which allows you to do more, right? As was shown by Cassandro Ferrari, Menor Presulti, Orlando Pico, and so on and so forth, which managed to prove a lot of results. Revisiting the construction by Froelich and Spencer, which is more or less abstract, has no physical meaning. And so they introduced something which are triangles, or more or less dipoles, as I was discussing with Pico yesterday, which is more natural, a more natural way of sorts of describing it. But there's some mathematical problems. So in his talk, he focused on the paper from 2017, and the happy coincidence is that the proof why triangles work if alpha is larger than 3 minus log 3 at base 2. Why is this a fortuitous coincidence? Because this number is smaller than 3/2. So using this representation, they were able to give a proof that there is phase transition, or rather that the phase transition is stable under a random field with a sufficiently low variance in a region. The problem was later closed 15 years later. I'll mention this en passant. And so about the limitations of triangles. So it's worth mentioning 2 works. First is Litting Pico, which show on the front of the limitations of the triangle representation that it is possible to make a bad choice of triangles such that the estimates don't work, regardless of how large you take the nearest neighbor's interaction. But the more important thing is the idea of the quasi-additivity, which is sufficient to prove phase transition and so on and so forth, right? And on another front, keeping the same representation, Bisacco, Endo, Van Enter, Kimura, and Russell gave a proof of phase transition without the hypothesis that the interaction between nearest neighbors is large, but they needed to restrict the exponential interval to something slightly smaller. Okay, so why revisiting the one-dimensional case is important? I write 2021, Kelvyn wrote 2025, because the paper was published in 2025, but it's been there since 2021, right? So the idea was adapting the Froelich-Spencer contours to the multidimensional case, introducing an extra parameter, and instead of using interfaces, right, like actual contours, incorrect points, which introduces some differences in the way things are represented, right? But it was very successful as a way of representing the problem, which is proved by Afonso, Bisacco, and Maya studying random fields if d is greater than or equal to 3. D equals 2, alpha between 2 and 3, and including 3, and d equals 1, alpha between 1 and 3/2 was closed by Ding, Huang, and Maya. I'll just mention it en passant. And then the extension of the same contours to different models with more complex spin spaces, right? Compact, but more complex nonetheless. And wait, did I do something? No. And then there are the ones that, so given the success in the multidimensional case, without the introduction that the hypothesis that the interactions are large, we revisited the problem. I mean, we proved stability. When I was writing the thesis, I also proved that if you dilute the interaction, phase transition remains. And then, more interestingly, we provided a converging cluster expansion, right? And it's a bit unfortunate that I mean, the more interesting things that I actually introduced I won't be presenting because they're highly technical, but the idea of summing n vertices and so on and so forth, I have never seen it in the literature, and it's I mean, it's technically beautiful, but it's impossible to present. So yeah, and finally, I mean, what I'm mentioning here, what I mentioned earlier, Ding Hong and Maya, right? So yeah, it's an esoteric result. Only the students may read it. So I mean, the Ising model is just a classical model on a lattice with spin space -1 + 1. The lattice is Z. I like to introduce boundary conditions in the definitions of things, because I mean, in this, it's sort of cheating. You're not defining it on finite boxes, but then on the whole space, but it's fine. And the ingredients of a classical interaction are two-body interactions and one-body interactions, an external field, and a two-body interaction which is invariant under translation. And as Kelvyn pointed out, it seems sort of ad hoc, but you need to change the definition of a Hamiltonian if you want to study the convergence of the cluster expansion. Yeah. Oh, no. J is a function of two arguments, so it's Z times Z. A two-body interaction is a function of two sites, right? X and Y, and you give the interaction between X and Y. Yeah. It's not important. But the point here is this. Of course, it's sort of natural to define the Hamiltonian in this way, because what you're actually interested in are excitations, right? So it's the box is sort of meaningless in this way. So the box arrives as something that is present in the definition of a Gibbs measure and so on and so forth. And once again, I recall that the partition function is not standardly normalized, but it's correctly normalized, right? And so as Arnaud mentioned in his talk, there's the Brownian unicity if beta is sufficiently small. So proving phase transition is simply showing that the extremal measures are different, right? It's standard. So about the way of representing contours. So first you begin with configurations which are functions from Z to -1 + 1. And the important thing, if your system is symmetric of sorts between plus and minus, is just knowing where configurations change from, I mean, there will be some pictures, don't worry. So in this way, you define this sort of dual configuration space, which is seen as the set of all. I mean, parts is always finite subsets. I don't think in terms of infinite subsets that are even, right? And so you want to know where your dual configuration sort represents where the important term with regard to the energy is concerned, and this is in the interior. So if you're thinking about a configuration which is plus homogeneous, then you want to know where it is minus, and if you're thinking of a configuration that is minus homogeneous, then you want to know where it's plus. And this sort of definition way of defining things, it's fine, it passes to boxes naturally, right? So here a silly example, you have a plus homogeneous configuration, and the dual configuration, its boundary of sorts are the spin flips, and the little losange are the interior of the configuration, right? And so you want to write things in terms of these this way of representing things, and of course the only term that detects the difference in boundary condition is the energy term. You renormalize things, so it's natural that it be symmetric if the interaction is purely two-body. And thus, you want to rewrite everything in terms of these things. So you had configurations, and you transform it into dual configurations, which are collections of spin flips of even cardinality. And then you want to write down the criterion for phase transition if in terms of these dual configurations of sorts, right? And now you get to Froelich and Spencer contours. So, I mean, what is the philosophy behind a contour representation? You want to represent every possible boundary in a way that that first, you actually represent the thing, which is condition one. And secondly, you want, two doesn't work if you're working with incorrect points, right? It's important. So for example, if you have something like this, I don't know, plus minus, there's something here, and then you have a minus plus, you cannot, remove this. This is not a configuration. It's, on the other hand, if you're dealing with traditional contours or this sort of disconnected contours, it works. So it's downwards closed in this sense. And of course, you want them to interact weakly. You're never going to have equality there because the system is long range. If you have a short range system, you can always, pack contours together to get something that separates perfectly. So the philosophy is quite simply describe configurations in terms of weakly interacting compatible drawings, such that if a collection of drawings is compatible, then so is any of its subcollection. And a contour is a minimal or rather irreducible drawing. Right? And the definition, as Kelvyn mentioned, is using the diameter because J depends on the distance, and the relative distance between things depends on the size of themselves. So a tiny comment here. In Froelich and Spencer, it's fixed, it's 3/2. In Kelvyn, it was A in the multidimensional case. This arises, so the philosophy behind was the stability, right, which he mentioned. You need to have something like this to have stability, right? So if you plug A equals 3/2 here, or rather, the proof from Froelich and Spencer only works so long as the exponent is less than 2. So this introduces a bound on the sort of, or rather this is 2 because dimension is 1. This introduces a bound to the alpha you can deal with, right? Which is exactly the bound that Cassandra Merola and the first one, the one from 2005, and then Pico later realized that you could adapt the thing to include a bit something a little larger. But you see, so you have to do things in a different way, right? You won't have stability in this sense. And here, you can't have it. So a contour is something you cannot partition. Oh, there will be a picture, which I mean gives a better description of sorts. And if they're sufficiently far away, then they are compatible. So you have this notion of compatibility depending on distance. So for example, if things are disjointed but close, then they're the same contour, which is something that I'll show. And a partition is simply a way of partitioning a dual configuration in such a way that two distinct elements are compatible, right? And the thing is, it's unique, right? So Imbri showed that it's unique. And if you change M, or at X maps to M, X to 3/2, if you change it for any function which is larger than X, larger than or equal to, you get the same thing. You get unicity, right? Uniqueness, sorry. So a silly example. So in the first one, you have a configuration which contains just 4 spin flips. They're sufficiently far apart, so they're distinct contours. If you consider another configuration where the middle spin flips are closer to the center but not so close, then you cannot separate them in components which are weakly interacting. They're the same thing. And on the other hand, if you proceed and you get really close to the center, now you have to separate them into different geometric objects, right? And so we proved energy subadditivity for contours which are external, which this is sort of like what Kelvyn was talking about. In this scenario, it's something simpler, but more nonetheless, I mean, if your system is long range and you have something, I mean, the pictures will describe it. So an external contour is something contextually dependent on the partition. It is external within the partition if it's not inside, if its interior is not inside any other contours, right? So for example, here in the top, both contours are external. In the second one, no, that's not the case. The blue one is not external, which are represented by the purple dot in the interior, right? So in this way, you can prove subadditivity. The trick comes from Litting-Pico, which is using, instead of absolute estimates in the way of trying to have a stability, you can't have a full proof In this way, you use relative things. So what's important is how things compare when compared to the Hamiltonian, right? Not in general. And so if you want to write down a Paulo's argument, you need to be able to count contours, right? And in this way, you cannot use the cardinality because there's no phase transition in one dimension, so it makes no sense to do so. You need this as a sort of involved definition, right? Which is you're gonna measure the size of a contour at different scales, sum over them, and cover is just the set of open coverings of A with radius 2 to the power n minus 1, right? And of course, this thing may have nothing to do with the energy of a contour. So, and of course, you have the same sort of sub-exponential bound, which is what you want. And here's the thing. You need a proxy for the energy, which is entropically reasonable. And I think this is the hardest, the most obscure idea from Froelich and Spencer. And, you know, it's very clever. So you're going to divide your contour into parts, subsets of the contour, within the contour, so subsets of spin flips, which are isolated. And the fact that they're isolated with the notion of irreducibility, which is a definition of the contour, means that it is odd. What does that imply? That implies that to its left and to its right, you have intervals of different sides and different spins, and thus they interact and they produce energy, and thus it is a good proxy for energy, right? So the thing is, you want to prove first that those different notions of entropy are equivalent, and it's here that you need alpha less than 2, so you need this. Otherwise, the estimate breaks down. I mean, as I was writing the dissertation, I thought of, you know, providing a counterexample. If you take the separating function exactly this, so x maps to x squared, but I mean, writing 30 pages of calculations, computations just to provide a counterexample to something that barely anyone cares about makes no sense. So I didn't do it. And finally, this is the important thing, right? It's a good proxy for the energy. This is, and now we have all the ingredients to write down a Paulo's argument. Very, very standard, very straightforward. You'll see it in a million books and so on and so forth, right? And in using this contour representation, you prove stability if the external field decays sufficiently fast. We don't know if there's uniqueness, if delta is very small, but I mean, okay. So it's time to get to the interesting part. So cluster expansion and decay of correlations. You need a notion of polymer, which makes sense to the model, which is simply a collection of contours such that every contour is external in that sense, and you need a notion of compatibility between polymers. There will be a figure too, but it's a little more involved. It generalizes the compatibility between contours, right? And you have this sort of technical thing such, so two polymers are compatible if they're disjointed, if their union is compatible, and one of the three conditions is met. Either their union is also a polymer, if the whole polymer is inside a single contour of the other polymer, and vice versa, right? And by definition, a polymer is not compatible with itself, and it's not compatible with the empty polymer, which represents the empty configuration, right? The ground state. So silly examples of I don't know, you could disregard the distance for a moment. Imagine they're sufficiently far away so that it describes an actual compatible, partition in terms of compatible contours. The point is that you're going to write your system in terms of, you're going to partition configurations in terms such that the elements of this partition are compatible polymers, sorry. And there are many ways to do it. And in this example, I just give the coarsest representation, which is the one to the right, and the finest one, which is trivial. I mean, every polymer contains a single contour, right? And thus, you can write the partition function formally. I'm not going to write down the activity. Once again, it's horrific. But the point is that you're going to You follow up, you follow with the usual Myers trick, you extract the aerosol functions. I referred to the talks from yesterday. And then you have dilemma, which, I mean, you could derive it from Penrose, a traditional graph tree bound. And here's the important thing. If you want to do decay of correlations by differentiating the partition function, or rather the representation of the partition function in terms of a hardcore gas of polymers, you need to have the things make sense for complex values of age, right? You want analyticity. You have to move away from the real numbers into the complex numbers. And the point is that this radius of convergence cannot depend on the polymer, right? So the thing is here that you get a radius that depends on the amount of times you want to differentiate something, which is A, right? And the temperature. So the higher the temperature, the smaller the radius. You're in finite temperature, so you always have a tiny bit of fat to burn, right? And there's the interaction. It's similar to the one previously. I'm more of a simpleton, so I like to define everything with positive signs. I don't like, I mean, I don't want things to be, to introduce sort of, you know, so that you need to keep track of what is happening in a way that is not immediately obvious, right? And thus you get this type of bound, which motivates the notion of sums over trees, which is a silly idea, but it's useful, right? So what are the ingredients? You want a countable set, you want a family of functions parametrized, but I'll also give the concrete descriptions, the concrete examples. And it needs to satisfy some natural hypothesis when you know what you're looking for, and now you have some weights on the edges too, right? And of course, and then there's this thing that I have never seen, the idea of introducing global compatibility, because if you look at this bad boy right here, you have a polymer, which is a collection of contours, and they're all compatible, and you have the sum of trees, right? So instead of having compatibility at the level of each edge, you have global compatibility, right? So this is what motivates the idea of V subscript I. And so what you're interested in is the weight associated to a tree, which is quite natural, is you just take the product of the vertices and the product of the edges, and so on and so forth. And what we're interested in is you want to fix a given number of values in the sum, right? So here, all indices that are larger than m are mute. I mean, you can rewrite them in a way that is convenient. And the good thing is that this infinite thing is formally finite. I'll be more precise soon, right? And as I mentioned, globally compatible sums are useful because of polymers and because lattice-sites are also globally compatible. So these are the examples, right? My way of doing things in the dissertation is sort of a graded way. So you go from polymers to contours, from contours to lattice-sites, and each one has a respective weight, which is natural in a way. So polymers, you just get the activity, or rather the uniform bound to the activity. Contours, you get the Boltzmann weight, and lattice-sites, everyone has the same weight, right? And the interactions are the edge functions. In the case of polymers, is simply incompatibility. In the case of contours, it's the interaction, if they are actually compatible in a way. And in lattice-sites, is this generalization of the interaction, which was introduced by Imbri. Probably not by Imbri, but I mean, it's where I found it. And so what you want to do is you want to be able to translate estimates from one degree to the other. So it won't make sense to most, I mean, at this point, you'd have to read the computations as to why it is the way it is. But essentially, the more complicated idea was that incompatibility between polymers needs to be translated in terms of contours. And this is done via this sort of thing. You could get something better perhaps, but since we're interested in a low temperature expansion, we are sort of, you know, less restrictive with regards to taking larger chunks of beta to make things work. And then you get something similar from contours to lattice-sites and so on and so forth. But the interesting thing and the funny thing is this lemma. the sort of finiteness lemma regarding types of trees. So a tree is special or contracted. You need two parameters, m and m, greater than or equal to 2. If every vertex larger than m has degree at least 3, right? Funny thing, of course, if n is equal to m, you just get all the trees with vertex set m. And the thing is that this set is empty if n is larger than 2m minus 2. And there is a tree always if n is equal to m minus 2. And this thing, this finite collection, when you take unions over all n, fixed m, allows you to write, so examples, right? The first one, the one to your left or to my right, is not an element of T star 7,5 because 7 has degree 2. And if you're thinking about the one to the right, then it is because 7 has degree 3 and 6 has degree 3, right? Ignore for a moment E bar and E, but the thing to keep in mind, more importantly, is the notion that it gives a formally finite description, which is the following, right? You need to sum over the weights, you contract things, you contract the edges, and you get this thing, right? And what does it mean? Like, what is the philosophy behind it? You want to fix m vertices. So what you expect to do m formal operations, right? So first, you need to deal with big W bar, right? So it's one formal operation. You need to deal with E bar, another formal operation. And then you have at most m minus 2 extra vertices. So plus m minus 2 formal operations, you get exactly m formal operations, right? And you get something similar for globally compatible sums. You have an inequality because it's not necessary that if you glue globally compatible trees, they remain globally compatible. But the thing is, I mean, we proved some results in the abstract scenario, and when you're thinking about locally compatible sums, it's sort of, you know, the traditional criteria for convergence of cluster expansion. So I'll also give a description of what this thing actually is in practice. The computation in this scenario is more of a Fernandez-Procacci flavor because we sum over generations of trees where you fix given the fixed vertex. The fixed vertex is the rooted vertex of the tree, and then you sum over generations. And but this criterion here looks a lot more like a Teskey prize, right? And these are the examples. So these are the manifestations of the abstract criterion for each class of objects. So polymers, contours, and lattice signs, right? And in the case, I'm not going to write down the hypothesis, but in the case of globally compatible sums, you get things. So the important thing here is you move from beta to beta half. You could do something slightly different, but the point is beta needs to become smaller at every step, right? So after each formal computation, you lose beta, right? Beta needs to be smaller, and if you do it m times, you get 2 minus m beta, or this sort of contracting transformation m times over beta, right? And the point is here, you had an infinite sum, and now you have a finite sum of weights, the weights you had before, right? And in this way, we can prove convergence of the cluster expansion. And the argument is sort of formal, a graded scheme. The abstract machinery is probably horrific. If you're used to the thing, you probably could do it directly, but I don't know, I find it aesthetic, sort of. So the first bound is quite literally rewriting the bound that arrived from the graph tree bound and uniformly bounding the activity. And then you sum over locally compatible trees of polymers with I can point, right? How the hell? Oh, cool. So you're going to sum over trees with a vertex fixed in position 1 equal to gamma, right? And then you get the activity, but beta needs to change to beta half, right? If you recall, Z bar, the weight of the contours is e to the minus beta half. So this is more or less equal to this, but you need to go to beta fourth. And now you sum trees of contours with a fixed vertex gamma, and you get this. And finally, you introduce invariant, or rather, equivalent classes of invariant equivalent classes of contours that are invariant under translations. And if you're in a box lambda, at most, the cardinality of lambda representatives of this class, this equivalence class are present, right? And so you get this sort of thing, and this is enough. You get sort of a uniform bound on lambda, which proves that the pressure is well defined as a function of age, right, not beta. And if you want to do correlation functions, this is the traditional, you know, summing over all trees which are connected. And I'm just going to write what we obtained, which is that it is bounded in this way. Something similar was already stated in the paper from 2014 by Cassandra Merola Pico Rozikov. And so what are the conclusions, right? So it's possible that employing this sort of technique, since we have the cluster expansion, we have, it's possible that all results should be extended, right? This way of doing things is probably problematic if you want to do phase separation for alpha equals 2. You need something very fine there. And on the front, another possible front is studying decay of correlations under the influence of a random field. And I guess that's it. 40 minutes? Good. And the references, you know. Some references, okay.
So the tradition is start with the people came from most distance. I think is Arnold. Okay.
Okay. Yeah, thank you. And I like the results, and somehow I'm mostly impressed by the fact that you could get rid of this alpha star restriction. You kind of mentioned the fact that it is somehow replacing absolute by relative estimates. Yeah. Can you explain that in a simple?
Yeah, the idea is very simple.
What is the underlying, like, insight or ID which makes it work?
So suppose you have a contour, right? If you want to bound, you want to bound this, right? And this guy is an external contour of this partition, right? So you want to bound this.
Basically, you want to kind of estimate how much it costs to put an extra contour in.
Exactly. And so you need at first, so this contour has let's say it has diameter d, right? So you know for sure that there are no large contours until, I don't know, m, d, 3/2, right? Yeah. Thinking of large contours. Yes. On the other hand, you cannot be sure of the rest. So technically, you need to bound it in a way that considers infinite contours that get all the way to the end from then on and from here on, right? And what is the idea? That it's not mine, it's from Pico, which is you compare, so you have the interaction is decaying, right? So R maps to the R is decreasing. So what you do is you compare the interaction of a point inside, and this guy right here is larger than the interaction between this guy and this guy. And this is true for all people here. You fix this guy, and you compare everyone with this one, and so on and so forth. And that's how you do it. So you get something like the interaction of this with what's outside, I don't know, gamma infinite or whatever. So you'd get something like this, right? It's something... something like this, using this idea times the Hamiltonian. So if you want stability, what you want is that this thing is uniformly bounded, right? And for that, as what I mentioned earlier, you would need to have a separating thing, the separating parameter, to be sufficiently large, right? It needed to satisfy, what was it? It's alpha minus 1, 2, right? It was this. But then you have the problem which arises from the Froelich-Spencer method. It demands that this part works for the entropic argument to actually work. So you need to do something else, right? And the something else is precisely the sort of, relative estimate idea, right? And then, in fact, you could, using this sort of thing, you can literally take any alpha between 1 and 2 and get the argument. And I imagine if you refine the arguments in multi-dimensions, you could literally take any A larger than D and it should work in a similar way. Doing the sort of similar, it's more complicated in that scenario, but the idea is more or less the same, right? Using relative estimates instead of absolute estimates. So instead of having actual stability, you have this thing that is not stable, but it's small compared to the energy, which is the quasi-additive property, right?
Can I ask another?
You can go forever. Not so far.
I was looking at the notion about essential decay.
Oh yeah, I mean, what I did was, it's sort of silly. You're writing down so why this came to be. So at some point, it didn't go anywhere, but I was curious about taking an interaction which is not regular, randomly diluting it so that it is regular in probability, and seeing if there's order or disorder, if the system is frozen, and so on and so forth. It didn't get anywhere. But then the natural idea is, well, what if you dilute a usual interaction? So essential decay is sort of like you have your J. So of course you're going to have no, I don't know if just from decay. No. So you have something like this, right? So JR is equal to a set. Sorry. And this set has satisfied some sort of density condition, right? So it's the limit. And I demanded 1 belong to A. And this is what? The supremum of, so it's N. Right. I prefer to do it like this, right? So you get something. So you have something which is sort of like a decaying potential, but with a positive density. It doesn't have to be 1, right? And it's easy to extend the argument of phase transition to that case.
Well, but basically, in those diluted parts, you kind of say you can change the interaction.
Yes.
But I think that what you wrote is you say that the J that somehow is smaller, but I think
no, it works if it works if it's bigger by a usual, GHS FKG argument.
Yeah.
But then I couldn't do the proof by contours. It's sort of a.
I think you need something that it should be smaller in absolute sense or something.
Oh yeah. Otherwise it's frozen. It's not regular, and you lose.
I mean, somehow if things are not completely ferromagnetic, it would be interesting to.
Oh.
It's in a way the advantage of contour arguments is that you may get rid of special symmetries like ferromagnetism or things like that, or reflection positivity. But then you should be careful that things don't decay too slowly.
Yeah.
And I think, I mean, the way you wrote it, you say it's less than. You don't want it to be strongly antiferromagnetic. Because then
Oh, there's no antiferromagnetic perturbation. I introduced a sort of, I just diluted the ferromagnetic part.
yeah.
Ferromagnetism, I have seen no study of antiferromagnetism using this sort of contour representation. Like,
Okay, because the way you wrote it, to me it was like.
it's positive, no? Did I not put
your hypothesis is one. That's not very clear.
Didn't I write it like this?
Yeah,
But then you make sure it's ferromagnetic, right?
The second thing that you remain ferromagnetic, you didn't write down.
This ensures that it remains
You only
ferromagnetic.
talk about ferromagnetism.
Yeah. But I mean, you could introduce I mean, it's not clear, because, you know, the whole thing is that you had the ground state from the get-go, right? So if you introduce antiferromagnetism, what is the correct way of you know, defining contours?
Well, the thing is, you would like to have the same contours, even if there's a very small perturbation.
Yeah.
But the proper notion of very small with antiferromagnetic terms needs some care.
Yeah.
But on the other hand, I think it's worth doing because to prove the phase transition, if things are ferromagnetic, you can do with correlation inequalities or comparing everything with nearest neighbor.
So essentially what you're saying is it would be interesting to do pure Gauss-Sinai theory in long range.
You don't even have symmetry. If you have antiferromagnetic, you still have spin flip symmetry, so it's kind of in between. It's not as bad as pure Gauss-Sinai, but still it will. There is something a bit complicated. Worth looking at.
There's the Froelich what? There's a paper like Froelich, Chase, Welsch studying introducing, you know, antiferromagnetic impurities in the one-dimensional in the multi-dimensional case from in nearest neighbors. But I don't think there's much done. Like in the multi-dimensional case, if you have for nearest neighbors, you get it for free for long range. But I don't think there's anything like that in the one-dimensional case.
The thing is, there are some no-go things which I've done, which Jacek has done. There is a thing by Giuliani, Liebman, Lebowitz, that if the decay is too slow, you kill the transition.
Yeah.
And so you have to kind of make some conditions that the decay of the perturbation should be faster than the decay of the original model. And if you like dilute, so you take like 1 out of every 100 distances. So you take out and you take something antiferromagnetic, it's fast decaying. I would expect that your contours should survive, but if they decay too slow, it doesn't work. So
that makes sense.
That I think would be kind of interesting, because they improve transitions for things that you don't know in other ways to prove. So that I think might be an interesting question. Yeah. What else? You say in the beginning somewhere that infinite Gibbs measures are limits of things you can get with boundary conditions. There are actually examples for which it is not true.
Yeah, your talk on G measures, but I mean.
No. There is an example by Lenin Kukier. If you take the sum of two Dobrushian states, left, right, and right, left, it's impossible to get it as a limit with boundary conditions.
Oh, okay. It doesn't. Then a silly question. What does this converge to in the limit? The Dobrushian boundary condition.
The Dobrushian boundary condition in one dimension, you just get the symmetric. You get a mixture of the plus and minus. Right. It's like in the picture of Georgie's book.
Yeah. Isn't it like this?
Yes. But if you do it in 3 dimensions, you take the plus minus and the minus plus, So
Oh, okay.
it's impossible to get.
Right.
So, so, that,
Yeah.
so that was another thing.
Even the
I know.
Japanese knew it, right?
Hmm?
Even the Japanese knew it before, right?
Yeah. Yes, there was a Japanese. In Japanese, there was an earlier.
Yeah, I mean, it's very funny because it seems that the first one, but he wrote only
In some Japanese textbook, and then Lauren got a letter. Well, the result is actually known, but then she said, well, at least some people have asked it, and it's worse to tell it also to non-Japanese people. Yeah, that's it. And yeah, you usually we discussed the history. I would say it's kind of interesting. It would be interesting to say that there are also different proofs. There's all the reflection positivity proofs, and I think Johansson also wrote some kind of contour argument. I never studied it, but I feel there is some similarity to the Fermi Spencer approach, but I don't know how similar it is.
Whose contours?
Kurt Johansson. He also did one of our R-square model.
Oh.
We didn't read. We didn't read that.
So I think it might be interesting to look at. Anyway, I think I'll pass it on to the.
I think yeah.
Okay, thank you very much. I like very much talk, and I will not ask technical questions about my manuscript, but you did it very well. I would be interested to understand what do you think about taking the case alpha equal 2 you did with the decay 2 and considering the plane rotator model.
Oh.
Perhaps you have no idea what's plane. If you don't know a plane rotator model, forget about it.
I mean, if you take this sort of model and you do a Fourier transform, you get a discrete spin set, right?
Yeah.
But then if it's not local, you cannot separate it. I mean, at the start, the plan was a lot more ambitious, actually. We wanted to do BKT for long-range models, right?
Mm-hmm.
But then the first step breaks down for obvious reasons. I mean, you don't have any sort of like current or height function or whatever representation for what are the configurations. And then you couldn't do much. We couldn't do much in the sense. So we got to the other Frill Spencer paper, right? But I'm not sure what will happen. I mean, this sort of thing, like it's as I mentioned, if in general you want, for example, people working in height functions, all they do is nearest neighbors, because then you do a Fourier transform and you get something that is once again sort of nearest neighbors. You don't mix things. You don't have interactions of infinite or rather an arbitrary number of finite bodies and so on and so forth. Then I'm not sure what would happen. I don't know.
Okay. Alors, another simple question. Sorry, I forgot it. I will get it. Yes. Okay. What's about the antiferromagnetic case?
So
the real one, because okay, you know the literature or you don't know. If you don't know, it's okay.
No, I mean the interaction.
It's not a problem. Okay.
I mean, you mean the long range, like something like there's no minus here, right?
Yes.
It's just sorry.
Okay, they are resolved by Kerimov, I would say.
Yeah.
You heard about Kerimov or not?
No,
Okay,
I mean
no.
what I checked is there was an old paper by Sinai where he computes the thing.
Yes, Burkov and Sinai.
Yeah.
They compute some strange quantity. Okay, it's okay. Just I wanted to have an idea about that. Sorry. Okay, I will stop.
Okay. So between Paulo and Aldo, okay. So Aldo is you.
Okay.
Okay. Well, first of all, congratulations for your talk, and congratulations also for the thesis, which is really terrible technically. Let's say it's very difficult to read. but so I'm not such an expert like Pierre and Arnaud about the one-dimensional case, which is also incredibly difficult to. And so my question is just related to the part of the cluster expansion and the part of polymer expansion. And you say that you apply the criterion which is similar to the criterion.
Yeah.
But when you presented, you start to present the partition, the Penrose identity, let's say. Once you have a partition scheme. First of all, I see that in your transparency you cited the right paper, but in the thesis I don't know if there is another version. But in the thesis,
there's a paper from '63.
Yeah,
the one
63.
I cited,
In '63, the partition scheme of Penrose was written in the '67. In the '63, there is the proof of the convergence via Kilbus-Salzburg, similar to the Ruel paper, which is in the same years. So when you apply, when you decide the partition scheme, then you say that it can be used to show an inequality. The sum of a row connected graph is less or equal than the sum of oval tree, basically.
Yeah. So in your work with Fernandez, you here you use the equality, right? So instead of you get this result, right? That the sum you would get something like this, right? It's minus 1 to n, the sum of rather trees that are fixed by the partition scheme, right?
Exactly. But it seems to me that you use this only
here.
Yes, only here. But how can I say? You because in the original paper by Penrose, he used it. He wanted to make this a similar proof that he do in '63. But directly, without using a Kilbus-Salzburg method, the equation, which is very heavy, let's say. He wanted to prove directly that the pressure was analytic in the activity, and he invented these things, and he wanted to prove it for potential which were not positive, because for positive potential was already proved by, I don't recall the name of the guy in the '60s. I don't know, but he wanted to prove for non-positive potential, and his idea is to prove for stable potential, but he was not able to prove for general stable potential, stability in the sense of a Ruel stability for potential, but let's say nearly. But he used more than he invented this partition scheme in order to do this, to prove analyticity of the pressure directly for non-positive potential. And so he invented his Penrose partition scheme, because this formula is old for any partition scheme, but you use it by only for polymer expansion, in which only for hardcore potential, in which the hardcore is positive, and for positive potential there is a direct bound. You can forget of the exponential in the Penrose identity because the potential is positive, and so the sum of all graph of connected graph is in modulus is less or equal the sum of all spanning tree. But this is the rota bound. But if you want something better, if you want something better also for positive potential, you can use the Penrose partition scheme, and you get, for example, you get something better than the Kotesia price criterion. So this is because in the end you have you manage to control the cluster expansion, and in the end the result is that the pressure is converged, or the 2-point correlation function can be written as an analytic series, and it's decay like the potential if beta is sufficiently large, and you have a beta, right? You can calculate beta or not.
It's terrible. I mean, you can. No, but yes, I mean, you can actually, at every step, you can optimize. So, for example, the first optimization is that is natural is here. You're going to choose, here, right? So technically, you could begin by optimizing this pair, right? And then you could optimize at every step and so on and so forth. But I mean, I didn't do it.
Yes,
someone with more, more courage.
My question is, in this method, it is possible to say there is a beta sufficiently large. The beta is this number. At least if you can say what explicit calculate this beta. Explicitly bound. It's possible to obtain an explicit bound of beta.
No, I do the compute. I don't do the take it sufficiently large, and the proofs. It is hidden inside the name of constants. They're like C1, C2, C3, C4, C5, C6, and it's hidden there. But technically, you could write it down all explicitly. It depends on M and alpha. But as I mentioned, you could try to optimize things and see what you can do. And for example, in the formal steps, right? As I mentioned here, right? I chose to do this type of contraction because I don't know, I like it. But you could try to optimize for the contraction too, and so on and so forth, right? And then it makes sense once you know that everything is going to work. If you if you don't have the proof yet that everything works, optimizing is something you do a posteriori, right?
Okay, no, exactly. I was saying this exactly because this beta could be improved using in a more efficient way the
of course, no, absolutely.
So, well, this is my only question because. So again, congratulations for your work. In the thesis, is also the introduction. It's really clear what you are doing in the thesis. Then there are technical part which for me is very hard to understand, but I know that there is a lot of work that have been done there. But it's also clear what you did in your thesis. Basically, you extend the results of the techniques of Flory Spencer in the region between 1 and 2. And this show, and again, this one should expect the 1 and 2 should be easier than 2, but it is not because this is. A model which is a little diabolic, let's say. Okay.
It is this part, right?
Okay, so I leave the Paulo. Okay.
It's this. It's hard.
First of all, I would like to thank Rodrigo for the invitation to serve on this committee. I also like to congratulate you for supervising this research. And well, Henrique, first of all, I would like to thank you for the nice presentation, and also congratulate you for your excellent piece of work. So I don't want to make you technical questions. So I have maybe two broader questions. One is the following. One of the main achievements of your thesis is the removal of the assumption that nearest neighbor interaction must be sufficiently strong. In your opinion, what is the key mathematical idea behind this achievement?
What Arno asked me. The thing was, so even though the hypothesis comes from percolation theory, when you're thinking about the right way of writing energy, you want to write energy in a way that is more pleasant than, you know, this. What does this mean? It's pretty involved. No, what does it mean? So what people wanted to do is simply, you know, you'd have a configuration, something like this. Oh, sorry, there needs to be another one. And then the idea was using, so for example, sorry, in many dimensions, right, multi-dimensional case, your contour is a closed, it's a closed curve which is homeomorphic to the sphere of dimension d-1, right? And what is the equivalent in one dimension is a dipole, right? You want to pair things. So this was from 2005, right? Cassandro et al. The idea was, so you have this thing, so you had a configuration, you take the spin flips, and what you want to do is you want to group it in triangles. I know, something like this. Disregard the matter of distance, something like that, right? And what you want to do is say, well, the energy of a configuration, which is now a collection of triangles, you know, T1, tau 1, tau 2, tau 3, right? The energy of this thing, using Pico's notation, you know, this guy is T1, T2, T3. You want to write it in a way that is it's on top of a constant, which depends on the decay, and summing over the triangles, right? In this way, it's the diameter of the triangle, right? So they wanted this much nicer representation, and of course, I mean, x to 0 is actually log of x, right? So they wanted this representation which is much nicer than this, right? You can actually make sense of this, but then to introduce this thing, they had to put the hypothesis that J1 is large. To have this sort of thing, J1 is large. That's why they needed to introduce, in this scenario, right? In percolation, it's something else. In percolation, you sort of ignore what happens in the first bound, and you just consider things depending on the limit, and that's from Eisenman, Chase, Newman, from '88. But, I mean, philosophically speaking, it's sort of weird. Like you want your system to be long range, but then for a proof to work, you get the nearest neighbor interaction to be very large. It's sort of, you know, and the way to fix it was, instead of trying to represent the energy in this much nicer way, was simply go to subadditivity. You just wanted, sorry, this, right? You just want this thing to be satisfied. And then the idea that allows you to remove the hypothesis that J1 is large is precisely the same sort of argument, where since J is decreasing, you just compare things with points that are further away with points that are closer, and then you get this sort of, you know, relative bound. And I did this the first time I wrote it down. It wasn't this way, right? But in the article, which is, you know, pretty terrible, to be honest, compared to what came to be the thesis. I mean, I learned long-range models reading Froelich Spencer. I had no previous experience. And then, you know, when time came to read the thesis, the crucial idea regarding energy, because the interaction decays, is just this relative sort of thing. You compare it with things that are to the left, or to the right, or whatever, but are further away, right? And that's how you can do it. You just ignore the specific character of the Hamiltonian. You just look at interactions, decay, and then you can do it, right? Relatively speaking, and relatively, like,
okay.
relative estimates.
Thank you very much. Well, I have no further question.
So okay, so I will not do any questions because I was part of this, and I will just let's say give some kind of a historical perspective of the thesis of Henrique. So the first thing that he didn't came to me, it was a friend of him, Lucas, that said that okay, Henrique wants to join our group. So one important thing maybe to mention here, that you see that I have a lot of students, but one a secret that people don't know, that most of them, they tried other people before, but nobody accepted. So sometimes I'm the third option, I don't know. And yes, I mean, this is very funny because in some way they know that they will finish if they come to my group. And actually more than half of my time is for I spend with the students, much more maybe. And then okay, Henrique came, and okay, we start to work, and I was doing a lot of things, and with maybe not with Arnaud anymore, but I was in Poland at some moment finishing papers, and Henrique stayed with the group, and then at some moment he was lost. So we did let's say a project meeting. So let's stop everything and try to pick up some very concrete problems. So we pick up the most thing that because after Bruno, which is here, Bruno did this step that to erase the first neighbor hypothesis, that which is here, with this idea that Bruno had this idea to use harmonic numbers and have a good estimate, but it's still with the triangles. And then Henrique was able to change exactly what Paulo mentioned, this way that to get the subjective, which actually is presented already in your paper with Litin. Actually, after we realized that you did already, we realized a posteriori, unfortunately, and this was the one let's say key moment of the Henrique thesis, that we just let's focus on the most let's say concrete problem that we should be able to go to solve, and then we wrote the first paper. I don't know, it is yes, this one, that now it was, we received some reports, but now we will they ask it to write a better introduction, and they will send to the referees now this first one. The second one just was rejected yesterday, and we already submitted in this night, and then let's hope a better choice. The problem is in mathematical physics, maybe when you do something very strong, but if you try to generalist journals, they say, here's mathematical physics, maybe it's too specialized. So we are trying to break this wall, but it's not so easy. So then we wrote this paper, and Henrique, as any PhD student, he oscillates, all the good students oscillates during the PhD, but unfortunately I think Thiago is not here, no, but Henrique helped us also in another paper with about C-star algebra and thermodynamic formulas. That's another topic that we do. and with Thiago. And actually, it's very nice that you mentioned that the introduction is very good, because if you look at the master thesis of him, there is no introduction.
It's terrible. It's terrible.
So he incredible improve the power to write things. The thesis, I agree that is very technical, because he chose this, let's say, let's say, some kind of technical in the beginning, which is his thesis. So he made this choice, but we checked, let's say, the details several times. This is another thing that. Because let's say my work with the group, since we have very strong group students, is not really do the calculation. The calculations, they are good. The SPR said yesterday, the most important job for me is to let's say, to organize that they should be able to work together. This is saying in this way, it seems easy, but it's not. I mean, the way that the university, they teach them to do, let's say, exercise lists, and get grades and so on, and the scientific parts to discuss and to write papers. For example, we did a lot of meetings, sometimes, and maybe more than 100 for a paper. And let's say maybe two pages make I don't know 8 hours to run to write properly 2 pages sometimes. So the thesis is very good, but I should emphasize that the thing that we have several challenges during this thesis, and for example, after the first paper, the GEMS asked me to give a referee report for a very technical page, 6th-page, very, very long paper. So I said, Henrique, you have to help me with this. So Henrique helped me to give this referee report. And in GEMS, you have to do very detailed reports for this journal. So he basically did the report. We did some meetings. And after this, he became very confident to come back in the problem of the cluster expansion, and then he was very much more confident, and then he solved it. So this was a very, very, let's say, we have a lot of different moments during the thesis, but the quality of the work is very, very good. And once again, as an advisor, and I started this project of to have a group. I don't know, 10 years ago, more or less. It's very successful, but sometimes people see the papers, but this is not the main part. Is not the I have to insist several times today to write papers, because they are very worried about to do the math, and they don't want to write the papers. Maybe it's boring, I don't know, but you have to check the details, and all the referees that we received, they say, very, very well written. So, and this they are going very good. So it was very, very successful, let's say, work. I mean, the results are very, very difficult, and but maybe the last thing that I should mention that Henrique is very strongly technically, but what happened with him? He is strongly based in a lot of good work that the group did previously. So we have Lucas Afonso thesis, which we are trying more or less mimic the flow expansion using diameters. So came João Maia with the random case that we use. This is the right definition with the volumes. So it's very good. All the theses are with all the details. So came Kelvyn. We did the cluster expansion. And also paper with Gilberto. So when Henrique arrived, we have a lot of very clean literature. So he was able to run very fast. That's so I have to emphasize that. Okay, Henrique has a lot of credit for his thesis. It's completely, it's wonderful the work that he did, but also the group and the other students that they are also responsible for the achievements, because we have a lot of let's say it's very difficult to read Florence Spencer and the old papers. So Lucas suffered a lot. Also, Henrique tried. I tried, but let's say I don't know an example. I don't know. In some moment, in the paper for expenses, they just mentioned use projections. So that's just this, and I don't know. It's sometimes it's 3 or 4 pages of a proposition, very technical. Now we know how to do, but in the paper is just use projections. So this is very good, but we are in a very good let's say we have a very good literature now that he could read, that was produced by the other students. So okay, unfortunately I have to ask that you have to leave a little bit, and then we have to decide. So okay, we discuss, and the unanimous decision is the Henrique is approved. So congratulations. so congratulations, and let's say. During this week, every student will receive a book, if you approve it, which is the case. So this is proportional to the thesis. So, okay, congratulations. It's okay.